All right, AP Calc, let's get going into section 3.3 here. And this is where we introduce the first of our rules here for taking derivatives of more complicated functions. All right, and so for this one here, I thought it would be a good idea to go back and just rewrite, maybe in a more succinct manner, 4 of the rules that we've already talked about before. It seemed odd to me that the author put them in previous sections when we start getting into rules right now. So the first few easy rules that we have here. Remember that the d dx, without a y right there, everybody, is an operator. It wouldn't mean anything by itself without something following immediately after it. So the way to read this, what I've written here on the left side of the equal sign here is the derivative with respect to x of c. Now the way we should interpret that is that c is a constant, and the derivative with respect to any variable, although in this case x, of a constant function is always going to equal 0. If you wanted to write that out in words, that's what you would put. The derivative of a constant is 0. Derivative means rate of change, and a constant function never changes. So its rate of change or derivative would be 0. Second rule, the derivative with respect to x of a times x. Now a times x, a would simply be any constant, x is the variable in question right now. This means that we're dealing with the derivative of a linear function. And the derivative of a linear function, we haven't really written this one out before, is simply going to equal its coefficient, which is just a. So the derivative of, for example, 4x minus 11 would simply equal 4. The rate of change of a linear function is simply equal to its slope, everybody, which is the coefficient, the number in front of your variable. Third case right here, the derivative with respect to x of c times f of x, which indicates that we have a function, f of x, multiplied by a constant value. And this is the constant multiple rule. This is the one that tells us the derivative of a constant times a function can be rewritten now as bringing the constant out in front now, and then multiplying that by the derivative of the function itself, which we would denote as f prime of x. So you can simply pull that constant out in front and then deal with it later after you've already differentiated the function. And the fourth rule here, the last one we're going to write on this slide, is the sum or difference rule. And once again, let me say, this is one you don't have to pay too much attention to. We tend to do it automatically without even thinking about it. That the derivative of a sum or difference is equal to the sum or difference of their derivatives. So the derivative of f of x would be denoted f prime of x. The derivative of g of x would be denoted g prime of x. And whatever sign you're doing with addition or subtraction in the middle, we do the exact same thing right here. So this is the rule that allows us to differentiate term by term throughout a polynomial function. So those are the 4 most basic rules for derivatives. Now we're going to get into the harder stuff today. And the first rule we discuss in section 3.3 is called the product rule. Now I do have to warn you guys, this is significantly more complicated than the quote-unquote product rule we had for limits. And in the limits, it simply said that the limit of a product is equal to the product of the limits. So it would be tempting to think here that the derivative of the product u times v was simply going to be, and this is mathematical jargon right here, you don't have to write this down, but you might think that this was going to be the derivative of u with respect to x multiplied by the derivative of v with respect to x. But it is not that easy, everybody. The actual product rule is more complicated than that. So the way we're going to do this is we're right now going to introduce a notation that your author and pretty much every calculus book I have ever seen over the last 25, 30 years uses the same type of writing. That u and v represent differentiable functions of x. So u is a function, not a new variable. That's important. And the same thing with v. You'll see that illustrated in just a second. And so the product rule says this, that the derivative of u times v is equal to the first factor, which is just going to be u, multiplied now by the derivative of the second factor. And the simple way that we denote the derivative of v is just going to be v prime. So it's the first factor, u, times the derivative of the second, v prime, plus the second factor, which is v, multiplied by the derivative of the first factor, which is u prime. And everybody, that's the product rule there. First times derivative of the second plus the second times the derivative of the first. Now, you guys are all smart enough to understand this. With addition in the middle right here between these two terms, there is of course the commutative property of addition that says that if you wanted, you could have written this in the other order. V times u prime plus u times v prime. I bring that up because a certain pre-calculus teacher, who a lot of you guys had last year, I know taught you the product rule in that manner right there. And it's not a question of somebody being right and somebody being wrong. I think you guys can understand this. Because of the commutative property of addition, both of these are correct. I understand why you might have been taught that second way down there. It'll actually make more sense a little bit later on in this section. But I always, kind of do it the way that I was taught it a long time ago, and I like it up there on the top. Both are fine and both are going to work. So it's probably better to memorize this in your head, everybody, verbally rather than symbolically. The derivative of a product is, let's walk through it again, the first factor times the derivative of the second factor plus the second factor times the derivative of the first. And let's see that in action, everybody. And as I very often like to do, we're going to start off with a problem that actually doesn't require this rule. Well, it does and it doesn't. We've been asked to take the derivative of a function written in factored form. 3x plus 2 times 4x minus 5. So this binomial factor right here, that's our u. And this binomial factor right after it, that is our v. But the reason I wanted you guys to start off with this problem right here is because there is a way to get around having to use the product rule on this. That said, I'm going to go ahead and use the product rule and then do it the other way to verify that that answer is right. So, looking at what was written, we're using the d dx operator here, the derivative with respect to x of 3x plus 2 times 4x minus 5. So this should be followed with an equals sign now, and here we go. The first factor times the derivative of the second. Well, the first factor is u, which is 3x plus 2. That gets multiplied by the derivative of the second. And of course, we can use our shortcuts now to take the derivatives of these polynomials. The derivative of 4x minus 5 is 4. And yeah, you could put it here, but I don't want you guys to get laughed at by the cool kids. So even though it's first times derivative of the second, it generally looks better to put that monomial factor out in front. First times derivative of the second plus the second factor, which is the binomial 4x minus 5, times the derivative of the first factor, which is 3. Now that's it. As far as applying the formula, we would always want to simplify if we could, though. We'll distribute the 4 and get a 12x plus 8. Here we'll distribute a 3 and get a 12x minus 15. And of course, we'll combine like terms to get 24x minus 7. And that's what we have, everybody, for the derivative of this function here, 3x plus 2 times 4x minus 5. Now, the great question to ask at the end of every math problem you ever do, did we get it right? And the answer to that is not quite clear because we don't know how to check that just yet. We got a new formula, we tried it, but we really have no way of knowing if we got it right or not, unless there's another way around it. And what we should realize, everybody, is that the factored function, 3x plus 2 times 4x minus 5, could be rewritten if we just took the time to FOIL out the original expression. So let's do that. The original function could be rewritten now as 12x squared. Let's see, outer product is a minus 15x. Inner product is a plus 8x. That's going to be a minus 7x. And the last product is going to be a minus 10. And so, therefore, how do I want to denote this, everybody? I don't love my notation right here. If I were to say that the original function here was f of x, let's do it that way, then I would say the derivative of that, f prime of x, would equal, well, we already know how to take the derivative of an expanded polynomial. That's just the power rule. The derivative of 12x squared is going to be 24x. the derivative of minus 7x is going to be minus 7, and the derivative of that constant, negative 10, at the end of all that is, of course, going to be 0. So that is the derivative without using the product rule, but having to take the extra step to go from factored form into expanded form, and then eventually down to this derivative here. But what I'm hoping you guys notice is whether we differentiated in factored form using the product rule or expanded form using the power rule, we ended up with the exact same derivative both times of 24x minus 7. So that ought to make you feel pretty good that we got that one right. All right, let's move on to another one. And this function right here is hopefully trying to get the point across that expanding the original function and then using the power rule maybe isn't the most efficient way to go with this one. You guys learned how to multiply a trinomial times another trinomial back probably in Algebra 2. And you may have done a little bit more of it last year at the beginning of pre-calc. It can be done, but it's a pain in the neck. And it's probably not the most efficient way to go about it. So what are we going to do instead? This is y, and now the directions would say to find the derivative of that. This is just something I like to do, guys. I like to put a dashed line in my work to indicate now that I'm about to differentiate. But of course I can accomplish that as well simply by good labeling. dy dx is equal to, and here we go everybody, this is our u and this is our v. So here we go. We start off with the first factor, which is 3x cubed minus 7x plus 4 times the derivative of the second factor. And the derivative of that second factor looks like it's going to be 18x plus 5. That's a binomial. And again, I could put this binomial either in front of the trinomial or after it. I think it looks better to put it out in front. So that's an 18x plus 5. So that's first factor times derivative of the second. Plus, here we go now, the second factor, which is 9x squared plus 5x minus 1, there we go, now gets multiplied by the derivative of the first, which looks like it's going to be a 9x squared minus 7. So that right there, everybody, is how the product rule works. And let's go ahead and talk about what I know you're all worried about right now. What do I need to do next? And what I need to tell you guys is probably the most vague and ambiguous set of directions I'm going to give you all year. And I feel sorry for it, but here goes. On these problems, when they show up on your quizzes or your tests in Chapter 3, I'm going to give you guys the very unclear, ubiquitous directions that are going to say, find the derivative and simplify as much as is reasonable. Those are horrible directions because reasonable is, of course, a qualitative judgment, but we're going to try to establish some criteria. Let me go back to the previous problem here, and let's talk about how after we came up with the initial derivative, what we did next. We distributed a monomial into a binomial. Guys, the distributive property, that's reasonable. So I would ask you to do that. And then from here, we combined like terms. That's reasonable as well. So if you had gotten to this spot right here and stopped, I would have dinged you a point or two right there because you didn't simplify that as much as you could to get us down to the 24x minus 7. Now, back to this one right here. If we wanted to distribute further, we certainly could. We would have to multiply a binomial into a trinomial using the old double distributive property. The 18x would get distributed in there, then the 5 would get distributed in, and we would combine like terms. Over here, likewise, we could do the same thing, distributing the 9x squared and then distributing the minus 7. Now boy, if we did that, that would get us a 12-term polynomial expression, if I'm not mistaken, and then we could combine like terms to get an expanded polynomial in simplest form. Everybody, I'm going to make the declaration right here that anything more complicated than binomial times binomial is not something that you need to do. So, binomial times trinomial, I'm going to say no to that. That's not something reasonable and efficient that I'd expect you guys to do. So I'm going to tell you something weird. We're actually done with this problem right here. I would give full credit for this version of the answer because simplifying it any further would involve something that we could do but would take a long time, and I think that's maybe a little bit unreasonable. So we're going to stop right there. Let's move on to the last example we're going to do together now for the product rule. And what's tougher about this one, I think you'll see right away, is that we have a three-factor expression, everybody, for our original function. So instead of just having a u and a v, we've also got a third one. I guess call it a UVW right there, and we'll go with that. Now, I'd still like to do this without doing any expansion on this. So the key to a problem like this is that you're going to have to decide to lump two out of these three factors together. And I don't think it really matters which one is which. So I'm going to go ahead and put a set of brackets around the first two factors like this, and the 7 minus x is going to kind of stand on its own. Now, in doing that, everybody, what I've now declared is that this entire factor here is u, and this by itself is going to be v. The weird part of this is going to come when we have to take the derivative of u, but we'll cross that bridge in just a second. Okay, so if that's f of x, I'm going to draw my dotted line here. You don't have to do this, but I think it's a good way to keep yourself organized. And I'm going to start finding my derivative f prime of x. So with this u and this v, here we go. The derivative of u times v is u times v prime. The first factor, which is 2x plus 1 times 3x minus 5, that's u, times the derivative of v. And the derivative of 7 minus x is just a negative 1, so I'll just put a negative out in front of all that. And I'm half done. That was u times v prime, the first times the derivative of the second, plus v times u prime now. The second factor, which is 7 minus x, now needs to get multiplied by the derivative of u. But here's where it's interesting. U is the product of two individual factors. So just to find the derivative of u, that's going to require the product rule within the product rule. And this is where these problems get confusing, everybody, is when you have to do rules within rules here. But again, I'm trying to find the derivative of u, and it just so happens that u is a factored expression. So here we go, everybody. Inside that first set of brackets, to find the derivative of 2x plus 1 times 3x minus 5, I take the first factor, which is 2x plus 1, and multiply it by the derivative of the second factor, which is 3. And I add to that, I'm going to skip down a line here, guys, the second factor, which is 3x plus 5, times the derivative of the first factor, which is a 2. So I had to use the product rule within the product rule, which makes it loads of fun. Now, what are we doing next, or what would we have to do next, and is it reasonable? Binomial times binomial, that's FOIL. Yep, and I've got some distribution and some combining like terms here. Yeah, that's reasonable as well. I'm actually going to hold off on the first one right now. You'll see why in just a second. And I'm just going to rewrite this as it was. The opposite of 2x plus 1 times 3x minus 5. The reason I'm not doing it there is because actually FOIL is the next thing I'm going to have to do over on the right as well. So I might as well hold that one off so these two are kind of at the same spot. 7 minus x times... All right, everybody, and we're going to do some things together here mentally. I'm going to distribute the 3, distribute the 2, and combine like terms. So the 3 times 2x is 6x. The 2 times 3x is another 6x. So that's going to get you a 12x when you add those two together. And my constants, 3 times 1 is 3, 2 times 5 is 10. The 3 and the 10 is going to get me a plus 13. Now, we're going to go ahead and FOIL both of these factored expressions here. So f prime of x equals, not only do I need to FOIL here, but I also need to worry about this negative out in front of the whole thing. So let's be on our toes. 2x times 3x is 6x squared. That becomes a negative 6x squared. Outer product is a minus 10x. Inner is a plus 3x. So that's a minus 7x, but the opposite of that is now a plus 7x. And the last product would have been minus 5. It now becomes a plus 5. Okay, moving on to the second part. This bothers people a little bit when the terms are out of order, but let's go ahead and do it the way we normally would. FOIL, first, outer, inner, last. So first, the 7 times the 12x is a plus 84x. The outer product, 7 times 13 is 70 and 21. That's a plus 91. The inner product, negative x times 12x is a minus 12x squared, and the last product here is going to be a minus 13x. Okay, little messy, and now combining like terms is certainly something reasonable to expect us to do as well. So where are we, guys? 7 terms here. Let's see what we can combine. We've got a minus 6x squared minus 12x squared. That gets us a minus 18x squared. That takes care of that term and that term. As far as x terms, we have 3 of them. 7x plus 84x is a 91x, and 91x minus 13x is going to get us a plus 78x. If I am not mistaken, let me do that another way. Yeah, that's right. And that takes care of the 3 x terms. And then our 2 constants are a plus 5 plus 91. That's going to get us a plus 96. So that's our answer, everybody. That's f prime of x in expanded form. That one wasn't easy, at least definitely in terms of the simplification at the end, but it was reasonable. So that's what we would need to do to get full credit on that. So those 3 examples, everybody, are what I was going to show you guys about using the product rule. It's not too bad once you get the hang of it, so let's try that homework and see how you do on it. Shifting gears now, we're going to move on into the quotient rule. And we write the quotient rule in a similar way to how we wrote the product rule, letting u and v represent 2 differentiable functions of x. So we're taking the derivative with respect to x of the quotient of u over v. And when we write the quotient rule, guys, the first thing you should get in your head is that the derivative of a quotient is a quotient itself. So I start with a fraction bar. And here's what we do. The numerator is messy. The numerator here for our derivative is going to be the bottom function, which is v, multiplied by the derivative of the top, which is going to be u prime. So bottom times derivative of the top, minus now, that's really important, minus the top times the derivative of the bottom. That's u multiplied by the derivative of the bottom, which is v prime, all over the bottom squared, which is v squared. One important thing to point out, this expression that we just came up with on the right uses 2 operations. It uses subtraction between the 2 terms in the numerator, and it uses division, as opposed to the product rule we talked about moments ago that uses addition and multiplication. Remember that addition and multiplication are the 2 commutative operations. And that's why, even though I like to write it this way, other people like to write it that way, and they're both fine. But because we are using subtraction and division within the quotient rule, this is the only possible way of writing it. I guess the only other thing you could do is rewrite this as u prime times v, and this as v prime times u, but I've never seen anybody do that. You can't change the order, though, of the 2 terms in the numerator. And this order, v u prime minus u v prime, is the reason why a lot of pre-calc teachers will teach you this version of the product rule. Because it's the same order with v u prime first and then u v prime coming second. It's just that this one has a plus in the middle and this one has a minus. So if that's the reason why you like to do the product rule that way, by all means, go right ahead, but they both work. This is the quotient rule, though, everybody. And we're going to do just one example, and I think you guys are going to get the hang of this one pretty quickly. Unfortunately, everybody, there isn't a great way to check the quotient rule unless I gave you one that could be factored and simplified, and then you'd just be mad at me for wasting your time. So what do we have here? A polynomial function on top and a polynomial function on bottom. Okay, so this is a quotient. 3x squared minus 7x divided by 11 plus 4x. So here we go. F prime of x will equal, and remember right away, say these words to yourselves, the derivative of a quotient is a quotient itself. And here we go. We begin with the bottom times the derivative of the top. Well, the denominator here is 11 plus 4x. And we multiply that by the derivative of the numerator. And the derivative of 3x squared minus 7x is 6x minus 7. This is binomial times binomial. It really doesn't matter, even for aesthetics, where you put the 6x minus 7. If you wanted to put it out front, you are more than welcome to do so. Okay, so that's bottom times derivative of the top, minus the top now, the numerator, which is 3x squared minus 7x, multiplied by the derivative of the bottom. The derivative of the bottom is just going to be 4, and I'd like to put that 4 out in front. So where are we, guys? Bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom, 11 plus 4x squared. So what could we do to simplify that is reasonable? We can do FOIL in the beginning of the numerator. We can do the distributive property in the end of the numerator, and then I think we are eventually going to be able to combine some like terms, and let's see where to go from there. So f prime of x equals, and this is the line that can take a lot of room. Okay, and once again, I've been a jerk today and I've given you things out of order, but that's okay. First product, the 11 times the 6x is going to be a 66x. Outer product there is a minus 77. Inner product is a plus 24x squared, and last product is a minus 28x. Over here on the right side of the numerator, we're going to distribute that negative 4 here and get a minus 12x squared and a plus 28x. Now, what I'm about to say next is important, so listen carefully. That denominator, 11 plus 4x quantity squared, could be expanded. What would it be? 121 plus 88x plus 16x squared. But everybody, don't. There is absolutely nothing to be gained by expanding the denominator in a quotient expression like this. Best case scenario, the numerator is going to simplify, and we'll be able to factor it and cancel something out with a factor in the denominator. But the denominator is already in fully factored form. I guess if you could pull something else out, like if that was a 12 plus 4x, you might want to do that. But there's no point in expanding it. That's going in exactly the wrong direction. So, I don't want to have to say this too many times, guys. Don't expand your denominators. Leave them in factored form. Okay, where are we going next from here? Probably not a whole lot further. F prime of x is equal to, I'm thinking we have some like terms in the numerator that we can combine. So I see a 24x squared minus a 12x squared. That's a 12x squared, and that term are gone. This was convenient. I've got a minus 28x and a plus 28x. That won't always happen, but those canceled each other out, leaving me with just a plus 66x and then a minus 77 at the end of all that. All over 11 plus 4x quantity squared. So now the only question we need to ask ourselves is, does that numerator factor? And if so, is 11 plus 4x or 4x plus 11 one of those factors? Now, there are some hints right here, some clues that might tell you whether this is worth your time or not. For starters, does this leading coefficient up in the numerator, 12, is that a multiple of your leading coefficient down here, which is 4? That answer is yes. Is the constant in the numerator a multiple of your constant in the denominator? That's a yes as well. So there's no guarantee, but that at least would seem to suggest that that numerator might factor and cancel with the 11 plus 4x on the bottom. So again, I'm going to make an assumption that it works but I'm going to verify that assumption. I'm going to go ahead and leave the denominator, 11 plus 4x quantities squared. And my theory, I guess my hypothesis might be that the numerator does factor and that 4x plus 11 is one of those factors. Now we're going to verify this. I'm not going to run with this assumption for too long, but let's see what happens now, guys, okay? All right. So whatever goes right here would have to multiply by 4x to make 12x squared. That would need to be a 3x. Whatever goes right here would have to multiply by 11 to make minus 77. That would have to be a minus 7. Now, all of this, up until this point, has been an assumption that we now need to verify. My real question is, did we correctly factor this numerator from here down into here? So let's check that, everybody. Does the first product work? 4x times 3x? Yes, it does. Does the last product work? 11 times negative 7? Yes, it does. But neither of those two things surprises me. I chose those blue numbers there, the 3x and the negative 7, so that they would work with the 12x squared and the minus 77. The real proof, everybody, is can we get this 66x here to work out with the outer and the inner products combined? So we need to check that. 4x times a minus 7 is a minus 28x. 11 times 3x is a plus 33x, which combine to make 5x, not the 66x that we needed them to be. So we took a shot, everybody, but that numerator did not factor into what we needed it to be able to simplify this expression. So let me be clear about what's happening. The numerator up here, let me point to this again, this numerator does not factor into this. So all of this was wrong. Now, is it possible that the numerator factors a different way? Yes, it is. I'm not guaranteeing that 12x squared plus 66x minus 77 is prime. It might factor. But the fact of the matter is, I don't care if it does, because it doesn't contain 11 plus 4x or 4x plus 11 as one of its factors. So even if it did factor into something else, nothing would cancel. And therefore, there's no point in trying to simplify that any further. So in spite of all of that work that we just did, the hunch that we had, the assumptions that we made, when we verified it, it didn't work out. So there was no point in going any further than, wow, this is taking a long time, than where we were, right? Wait for it, right there. That's as good as this answer is going to get, everybody. So we tried to factor and cancel, but I'll tell you right now, to ruin the suspense, that doesn't usually work with the quotient rule. If it does, what that actually usually means is that there was some simplification that could have been done in the original expression right over here that we may have missed. So my advice to you guys, this doesn't happen very often, is if the original expression, the original quotient, if that can be factored and canceled or simplified in any way, you should do that immediately at the beginning before you start differentiating. Always easier to simplify first before doing a derivative. As it is right now, we went ahead and did this whole thing, and that final answer that we came up with couldn't be simplified at all. So, to use a phrase that gets overused, it is what it is, guys. It's ugly. It's not going to get any better. All right, that's as much as I was going to do with you guys for the 3.3 notes. Hopefully not too bad of a section for you. So let's give that homework a try and see how we do. Good luck, everybody.